This is 5.2, and this is relating graphs to situations, and there's only actually one concept for this lesson. So today we are going to look at some pictures of graphs, and we're going to relate them to situations, or we're going to look at problems, like word problems, and draw a graph that shows what it's saying. So here we have a situation with some graphs to follow it. It says Jenny leaves home and drives to the beach. She stays at the beach all day before driving back home. Which graph best shows the situation? So we have some keywords we need to look at. She drives, oh, we're going to put that in a different color, to the beach. She stays at the beach, and then she drives back home. So if you look at these words, you have time, let's do another color for these, time down here, and then you have distance over on the side. And that distance is from home. So we are going to be driving away from the beach, or not away, to the beach. So our distance from home is going to be greater the further we get from home, or the more time we spend on the road. So that's going to be caused by an upward line. Okay? The more time on the road, the further we get from home. So if you look, this first graph and the second graph both show that the further you're on the road, or the more you're on the road, the further you are from home. This last graph, it tells you that your distance from home was really high. These two graphs show you starting at home at 0. This graph shows you starting at a distance away from your house. So this one doesn't work. So now we're between A and B. She stays at the beach. No, she stays at the beach. She's going to be there for a certain length of time, but her distance from home is not going to change. So that is here with this line. Now, graph A shows an upward and then a downward, but it doesn't actually show that she stayed at the beach at all. That's like you drove to the beach, you turned around and you came home. Graph B, though, shows that she drove to the beach and she spent some time on the road, and her distance from home got further and further. But then it flatlines and say, oh, she spent some time at the beach, but while she was at the beach, she didn't get any further from home. And then she drove back home. So as she drives back home, she's going to get closer to home. So it's going to be a downward. So if you look at this, we're going back down till we get back to 0, which is her home. So she started out at the beach, and the more she drives, the closer she gets to home. So graph B is our answer if we were going to say which graph showed the situation. So this problem says the height of a tree increases over time, but not at a constant rate. Which graph best shows this? So we have our height over here, and we have our time down here. That's supposed to say time. I don't know what happened there. Now, if it's growing, it can't just be a straight line, because this shows that it isn't growing at all. In fact, that's just saying it is staying the same height. It's in the ground for, let's say, 8 years, and it's still the same height as when it was in the ground for 1 year. B, however, shows that when you planted it, you put the seed in the ground, and as time went on, it got higher and higher and higher. So, year 1, it was much shorter than year 6. Year 6, it was much higher. So that shows that it increases over time. But a constant rate, this here is a constant rate, meaning it stays the same height. If you look at this one, you can see that some years it grew more than other years. So that means it's not a constant rate. Kind of like us. We grow more at a younger age, and then as we get older, we start not growing as much. So our bodies are kind of like B, so you can relate it to that. Now we need to look at a word problem. So, Maylee and Katrina traveled 10 miles from Maylee's house to the movie theater. They watched a movie and then they traveled 5 miles farther to a restaurant to eat lunch. After eating, they returned to Maylee's house. Sketch a graph to show the distance from Maylee's house compared to time. Use your graph to find the total distance traveled. So, we are going to draw a little graph here. And we are going to put time down on the bottom. And we are going to put distance here. So this is kind of like the beach problem. So they started, we're going to say this is 0. They were 0, 0. That's the origin. They were at Maylee's house and they had not spent any time driving. So they traveled 10 miles. We need to get some little coordinates on here. And you only need some coordinates on the distance because it gives specific distances they traveled. So it says, where'd they go first? They went to the movie theater and they traveled 10 miles. Well, if they're traveling 10 miles, over time they're going to get there, right? So we traveled 10 miles. So here we went to movie. Then they watched the movie, and just like when we went to the beach, their distance doesn't change. They don't get further away from Maylee's house, but they do spend more time. So it's a straight line. So this is watching movie. Okay. Then they travel 5 miles farther to go to a restaurant. So at that point, they're getting further away from Maylee's house. So this is traveling. But again, while they're eating, they're not making any distance from Maylee's house. So we have a flat line. So this is while they're eating. And then they went back to Maylee's. So they're going to go all the way back to Maylee's, which is at our starting point. So we also want to find the total distance traveled. Well, we know they traveled 10 miles to the movie theater. We know they traveled 5 miles farther to the restaurant, which gives us 15 total miles of going places, and then they had to go home. If it was 15 miles between the movie theater and the restaurant, it's going to be 15 miles home. So we have to add 15 to that, and we get 30 miles total that they traveled. So here's another story problem. Jared parked his car in the supermarket parking lot and walked 40 feet into the store to the customer service counter where he waited in line to pay his electric bill. Jared then walked 60 feet to the back of the store to get 2 gallons of milk and walked 50 feet to the checkout near the front of the store to pay for them. After waiting his turn and paying for the milk, he walked 50 feet back to his car. Sketch a graph to show the distance from his car compared to time. Use the graph to find the total distance traveled. So again, we're going to draw and we're going to have time down here. We're going to have distance here. And since it gives us specific markings or specific feet away from his car, we're going to have some distances here. So we're going to have, let's see, 20, 40, 60, 80, and you can make these at any intervals you want. That's the interval is 20, 40, 60, 80. You could go by 10s, you could go by 5s. Just kind of depends on what you want to do. So, the first thing we know is that he walked into the store parking lot, or walked into the supermarket, and he walked 40 feet. So, it took some time for him to walk the 40 feet, right? So, he's going to get further away from his car in those 40 feet. So, this is where his car is. Then, he paid his electric bill, and then he walked to the back of the store. But while he was paying his electric bill, he waited in line. So while he waited, our time flatlines, but our distance doesn't go up because he's the same distance from his car. And then he went to the back of the store, which was 60 feet. So from 40 feet, he went 60 more feet. 40 plus 60 is 100. So as time went on, he got further away from his car. Then it says that he walked 50 feet to the checkout near the front. So 100 minus 50, because we're getting closer to his car, is 50. So he walked here, and now we're at the checkout line. But he had to wait in line at the checkout line, which means the time got longer, but his distance from his car didn't get any longer. And then, once he was done waiting for his turn, he walked back to his car. So he got closer and closer and closer to his car. So it says, use your graph to find the total distance traveled. Well, we got 40 feet here. This was 0 feet. Then we went from 40 to 100 feet. That's 60 feet. Then he went with his milk to the front, and he had 50 feet. Then we flatlined again. He didn't move at all. And then we went from 50 to 0 feet, so we had 50 feet again. So we add those 40 plus 60 plus 50 plus 50, and that equals 200 feet. You could also just use 40, 60, 50, and 50 right there. So the red is to store, blue is waiting, green is to back, yellow is to cashier, red, well, he's waiting, and blue is to car. So, that's how you do it.